Hello everyone and welcome back to the channel. And today I have this epic head-to-head comparison between these two graphics cards that are plugged into my test bench over there. I have an NVIDIA RTX 5090 and also NVIDIA RTX Pro 6000 Blackwell GPU. So now this is not a glitch that you saw. Yes, I indeed have two of RTX 5090s and two of RTX Pro 6000 Blackwell GPUs. It does open opportunities for me to do way more with this 250 gigs plus of VRAM that is plugged into this test bench. All right, this video is going to be long and I want to do justice with the three main inferencing techniques that I want to do. Number one, LLM inferencing using llama.cpp. Number two and three will be ComfyUI pipelines for video generation and text generation. I'm only going to be covering llama.cpp and the text generation in this video, whereas video generation will be covered in the next video that I will be doing. There is a lot to cover and I would not want to waste your time. So I'll timestamp everything in the description section below so that you can jump forward to any section that interests you the most. To start with, first, I'll kick things off with a detailed overview of our contenders and the absolute beast of the test bench that I've built over here to push these two graphics cards to their limits. And then I'll cover the hardware specs and the architectural differences between these two graphics cards, what sets them apart, and then I will dive into the core of our testing. So starting with a head-to-head comparison on the LLM with llama.cpp, how does the processing and the prompt processing and some other configurations differ? And why just a little bit more VRAM can help you out over here. And after that, we will move into the visual domain and we'll do some image generation testing. We'll be using, of course, this most popular Flux Context model over here for image editing. Using ComfyUI. The video generation using the Onion model will be the next video. I don't think I'll do justice if I cover that in this particular video. And then in the end, I'll wrap it all up with our key insights, use case recommendations, and then the final verdict on which card is good for whom. All right, there is a lot to cover. Let's get directly into it. Both these GPUs, 5090 and 6000, are built on the revolutionary Blackwell architecture, but they represent two fundamentally different philosophies. One is for the enthusiasts who want to push every limit on the consumer grade hardware, and another is for the professionals who demand absolute precision and scale. The question we are answering today is not just which is faster, but which is the right tool for your AI workflow. And we'll dive deep into their architecture and then we'll push them to their breaking point with the real world AI benchmarks. But I wanted to give you a high level overview of what these cards actually are. At the heart of both these cards is the groundbreaking Blackwell architecture, which is fabricated on a custom version of TSMC's 4 nanometer process nodes, which NVIDIA calls 4N. But not all Blackwell chips are created equal. RTX 5090 uses GB202 GPU, which is a monolithic die, and it is in itself a marvel of an engineering. It is measuring a massive 750 square, and the RTX Pro 6000 is based on a larger, more feature-complete version of this Blackwell silicon. And this allows NVIDIA to enable more of the functional units on the die, resulting in higher core count across the board, which will be the theme that you will see across the board over here. And let me show you the comparison wise how both these cards look like right on NVIDIA's website. So one thing you will notice is, like I said, at the heart of both these GPUs lies this NVIDIA's Blackwell GPU microarchitecture. Blackwell is the successor to Ada Lovelace, and it includes several major advancements, which is tailored for AI and high-performance computing. Now, both RTX 5090 and RTX 6000 Pro leverage this Blackwell architecture, which means they share the features like 5th generation tensor cores and 5th generation ray tracing cores. And both cards can accelerate AI operations with ray tracing more efficiently than the previous generation, the RTX 4090. RTX 6000 Pro is essentially a fuller realization of Blackwell silicon, whereas the 5090 is slightly a cut down version of it. So where are the differences? So let's talk CUDA cores, the basic FP32 shader units, and SMs, which is the streaming multiprocessors. So GeForce RTX 5090 comes with 21,760 CUDA cores enabled, which corresponds to about 170 SMs out of 192 on the chip. Now, in its big sibling, the 6000 Blackwell, we can see the full might of this silicon, 24,064 CUDA cores. Now, all the 188 SMs are firing on all cylinders over here, which is massive. So out of 192, 188 SMs. That is indeed insane. This is about 10 to 11% increase in core count for the Pro card, and these cores contribute to the raw computing horsepower of the GPUs. So for example, in terms of single precision throughput, RTX 5090 is rated about 105 T-flops, and it boosts clocks to about 2.4 gigahertz, whereas RTX 6000 can push roughly 125 teraflops with FP32 at the similar clocks. So purely on paper, the Pro has a slight edge in raw compute in the order of 10 to 15% higher T-flop owing to those additional SMs and possibly a binning that allows equal or slightly higher clocks. Now, crucially, for AI tasks, Blackwell introduces lower precision math capabilities. So both 5090s and 6000 Pros, they support FP8 and even FP4 data formats. Now, this is huge for AI inferencing because 4-bit floating point processing is massive for neural network tasks. It speeds up the memory savings and it also speeds up the computational times. NVIDIA's second generation transformer engine on Blackwell uses a technique called micro tensor scaling, which is what enables the 4-bit precision without losing any accuracy. And in fact, Blackwell's FP4 support can double the performance and the model size compared to 8-bit on the same memory footprint while maintaining very high accuracy. Both 5090 and 6000 share this capability. So you're not losing out if you get one or the other. However, I wanted to mention this for completeness. Besides the tensor cores, RTX 5090 and 6000 also have ray tracing cores. And there are 170 versus 188 in 5090 versus 6000. We'll not be doing any ray tracing comparisons today. We are not going to be playing video games over here. We'll be doing AI inferencing using these expensive graphics cards. So this won't affect our AI benchmarks, but it is definitely worth noting for completeness. The ray tracing cores are 4th generation, meaning improved ray triangle intersection throughput, and they support features like ray reconstruction, which is an AI denoising feature which came with DLSS 3.5 plus. Now both cards inherit the support for NVIDIA's new DLSS 4, which includes the multi-frame generation. Both these cards will be amazing in your gaming context. Both are extremely advanced. The 5090 for consumer use, 6000 carrying those features into professional visualizations as well. Both the cards will do just fine in any of your intense gaming tasks. Well, if everything on these two cards is almost the same, what's the catch? Memory. Both its size and speed, which is arguably the biggest differentiator between these two cards. If you remember one spec from this video, Let it be this. RTX 5090 has 32 gigs of GDDR7 VRAM, whereas the RTX 6000 Blackwell has a whopping 96 gigs of GDDR7 VRAM. Yes, you heard that right. It's 3 times more, 96 gigs on a single card. That's triple difference in memory capacity, which is huge for especially AI related use cases when you're trying to load these huge, humongous models on the video RAM. Both cards use the next generation GDDR7 on a 512-bit memory interface. Now, that wide 512-bit bus is a step up from 384-bit bus on the previous gen cards that we had, 4090, 384 versus 5090 and 6000 at 512-bit bus. Now, with GDDR7's improved transfer rates, each card achieves about 1792 gigabytes per second. So this helps feed all those cores, those 20 plus thousand cores on these two cards. In fact, 7092 gigabytes per second is roughly 70% higher bandwidth than RTX 4090 had. And RTX 5090 and RTX 6000 actually have the same bandwidth because they run the memory at a very similar speeds, which is around 28 gigabits per second effective. And both of them utilize the full 512-bit bus over here. So in terms of raw memory throughput, neither card has an advantage. They both can move data in and out of VRAM at the exactly same blazing fast rate. The difference in capacity and configuration is that the 5090's 32 GB comes from 16 memory modules of 16 gigabit, 2 GB each, populating the 512-bit bus. Whereas the 6000's 96 GB is achieved with a higher density modules and possibly a double-sided PCB. And it has 3 times the memory capacity, which is reportedly implemented at 12 GB per 32-bit channel. Perhaps they stacked up more modules on top of each other. We saw some pictures online of RTX 6000's PCB. It's very busy and crowded with the memory chips on both sides. Also, one difference is that it's ECC memory on the Pro card, which is a feature professional users expect for reliability. The RTX 5090's memory is non-ECC, which is the standard for consumer-grade GPUs. What does this all mean in practice? Well, for one, large AI models or higher resolution buffers that simply cannot fit in 32 gigs will fit in 96 gigs. For instance, if you're working with an enormous 3D scene or a gigantic LLM that might be 60 plus gigs, like these 72 billion parameter models at the FP8 Precision, they may not fit in 5090. 5090 would struggle or require quantization or offloading, whereas 6000, it can accommodate it directly. So the 96 GB card is definitely worthwhile when you are playing with a lot of these video RAM heavy tasks, which exactly what these AI tasks are for us. The last thing that we have is our test rig, which is built on Asus Pro WSW790E Sage SE motherboard. This is a high-end workstation motherboard using Intel's W790 chipset. Now, this board is critical because it supports 7 PCIe 5x16 slots, meaning we can run 4 double-wide GPUs, which is what these graphics cards are, at full x16 bandwidths. And this is done without starving any one of these GPUs to X8. Now, the CPU is an engineering sample of Intel Sapphire Rapids, which is 56 cores and 112 threads. And we have total of 512 gigs of ECC DDR5 RAM installed running at 4800 megahertz speed. We have run the CPU in its default configuration, so no overclocking to preserve stability for long-term AI runs. And the cooling is done using a very nice air cooler from Noctua. All right, let's get directly into LLM inferencing. And we choose llama.cpp for learning the large language models over here. Specifically, I would like to run Gemma 3 model, the 27 billion parameter model, quantized in 4-bit and 8-bit to demonstrate a point over here. And this will also maximize the GPU usage for us. Now, llama.cpp was primarily a CPU-based framework, and it was designed originally to run llama on CPUs with quantization. But it has evolved and can offload parts of the model to GPU now. And if you can offload the whole model to GPU using libraries like CLBlast or CUBLAS. In my tests, I've leveraged full GPU offloading for these large models to measure the GPU's impact on inferencing throughput. So what I've done is I've compiled llama.cpp, and I'm going to quick switch to my remote machine over here. So I've already compiled this llama.cpp right here, and it is ready for us to start the inferencing process. So step one would be for you to download the model. In my case, I've just put the model into my home directory dev.ai models and ggml.org. And the model that we are taking a look today is Gemma 3, and also this MMPR OJ model fp16.gguf. So you need the second file over here if you also want to do the image inferencing. So Gemma 3 model does both text to text and image to text, which is what we need this second gguf file for. So similar to that, you will see there is a Qwen 2.5 model also over here. We'll see if you want to do Qwen, but I definitely want to do Gemma to prove a point. So let's go ahead and first run this particular Gemma model. And I'll take this Q4 quantized model, as you can see over here, and we'll try to load this on our GPU. So to load this, the easiest thing to do is to define which particular CUDA device you want to load it on. So I want to load it on the CUDA device 2. Now, there is a catch over here. And let me show you this. If you take a look at CUDA device 2, it looks like the CUDA device 2 is Pro 6000, right? RTX Pro 6000. But I don't know why my GPU numbering is just messed up. So 0 and 1 are apparently 2 and 3, and 2 and 3 are apparently 0 and 1. So this is just flipped, and I don't know why. In the scripts, you will see anytime when I use 0, I'm actually referencing to 2. And anytime when I use 2, I'm actually referencing to 0 over here, right? So 0 is 6000 and 2 is 5090. I mean, I hope it's not confusing, but you will see the models being loaded on these GPUs over here accordingly, and then you will find out. Okay, so the very first model we are attempting to load on our 5090. So I'm going to copy and paste this command, which is saying to take this model name, give it an alias of this, and this is the MMPR OJ file that I showed you, this MMPR OJ name, and then the context size of 16K, CTK, and CTV. So it is the KV cache that is at the Q8. And then there are some batch and unbatch, how many GPU layers I want to offload. So all of them I want to offload. Jinja is for our tool calling over here. I just need one parallel thread, like so only one request at a time. And then 56 threads because this is having 56 cores. Host name of 0000, meaning external access is allowed, and the port name of 10,002, right? So I'm going to copy this and then I'll paste it over here in the terminal and let this model load while I take a look, and the model completely finished loading now. Okay. Now that the model is loaded over there, let me open Web UI, which is actually hosted on 4090 port for me. Okay, perfect. So I'm gonna choose the model as this particular model. You can see this is this external model that is available. Hey, how are you doing? Then of course it's gonna reply back. 156 tokens per second of prompt processing, and 67 tokens per second of generation time. And this is for 5090. Right, so this is a very simple prompt over here. So what we'll do is, I don't like this. I actually like to do like a lot of processing, prompt processing, and then see how it behaves. So I'm just going to do a Control A C of this whole GitHub first page that they have. And you know what? Let's just send it back to the model and see what does the model say. So I'm going to send it. There we go. And you will see that the first GPU 5090 where it is loaded is going at full 90%, 100% over here. Okay, all right. So it did whatever it was able to process and generate some tokens. And let's take a look. So there were 8,941 prompt tokens, and total tokens were 9,200 that it generated along with the total initial tokens. Let's take a look at statistics now. So we have 3,595 tokens per second for prompt evaluation time and 63.49 tokens per second generation time of the tokens over here. All right, I'm going to just close this, Control C, and get out of this. And what I'll do is run the same model on 6,000. All right, I'm going to go and modify this command over here and change it to GPU 1. Okay, hit enter, and we can see that this particular GPU theoretically should be loading the model now. And yes, it did. Awesome. Perfect. So this model is now loaded on our RTX 6000 GPU. And I can go ahead, do a reload. Let's start a new chat. The model name stays exactly the same because we have just switched the GPU on which it is loaded. Okay, let's do very simple. Hello, hey, how are you doing? And I usually do this so that I can check how much is the prompt processing and token generation with a very small prompt, right? So let's go ahead and see. For a very small prompt, it is 270 and 61 tokens per second. Okay, all right. And the second thing we'll do is just copy and paste this huge GitHub. Oh, no, not here. Okay. Command A, C, and then just send it back over here, some 8,000 tokens, and see how much does it take to process it. So our RTX 5090 versus 6,000 comparison is live right here. Okay, so we have again about similar number of prompt tokens, 8960, and the total tokens of 9,200, right? Moment of truth. Let's go and see. Very, very similar performance. Exactly same performance over here. We see 3956 for our prompt evaluation time, and then 62.71 for our token generation time, right? So this is the pure text capabilities that we see over here. Okay, I also want to compare the image to text capability, right? So because Gemma models have the capability of being multi-model, so let's test that. Exit out of this, go up, and then one more up. And I want to make sure that the CUDA visible devices is 2, which is our 5090. Hit enter, and loading this model on 5090 back again. Right? And I know that there is a tool called Llama Swap that can do all this for me too, but we are just using it manually over here today because we just want to visualize everything right now manually on how to do this. So let's take an image from internet, and which image should we take? So we'll just say Taj Mahal. And we'll just take a random image of Taj Mahal. This is fine. So a random image with a random person of Taj Mahal. And we're gonna save the image as random image. Okay, perfect. Let's start a new context. So we'll send that particular image, and we will send this random image to the model and say, what is it? Right? And let's just send it and see what the model does. Okay. That was fast. So you can see the model really worked super fast over here. Wow. I'm gonna try to see 581 tokens per second and 63 tokens per second for prompt eval and generation. So this was nice. I mean, I think it's the same speed that we are seeing for the text. It converts it, tokenizes it, sends it back. So the generation speed for text remains the same. All right, we'll Control C and we will now load it on RTX 6000. Let's see if it is loading on 6000. Yep, it is loading on RTX 6000. And I'm gonna just send this thing back over here to the model, right? And let's see what happens. Perfect. So almost the same response. Let's see. 787 and 63. So it is almost the same thing. Yeah, and this is expected too, because for LLM inferencing, when the model can fully fit into the GPU's VRAM, nothing major is going to change over here. There's only 10% difference in performance theoretically, which is actually not even translating it exactly over here for us. Okay, why did I choose the Gemma 327 billion parameter model in Q4 quantization? Because I wanted to show you the difference between 5090 and 6000. At 4-bit quantization or these Q4 models, you can fit both the models easily on any one of these two cards, right? So you saw about 20 gigs of VRAM was utilized and it fit on the 32 gigs card just perfectly fine without any issues. However, what happens if you want to load a Q8 quantized model? So first we'll attempt to load this on 6000 card and you will see it loads, and it loads perfectly. Yes, of course, it took a lot of VRAM over here, right? So this particular card already had 18 gigs for a ComfyUI workflow that was running in the background. So close to 39 gigs of VRAM is required over here. For this model, we'll have to choose this Q8 quantized model over here, and I can do a regenerate to see how much speed that we get. Of course, a Q8 quantized model will be slower. So instead of 60, we are seeing 41 tokens per second over here now, right? So this makes sense. Of course, this is supposed to happen. We'll also go back to one of our old prompts. We'll send this whole prompt to the 8-bit quantized model, and it should take longer time to process it too, right? Prompt processing would be longer, and the token generation would be just slightly longer too. And we'll let it finish, and then we will go to our 4000 tokens per second for prompt eval time, which is, I think, slightly higher than what we had for Q4. Interesting. And we have the prompt generation time of 39, which is definitely lower than the 63 or the 65 range that we were seeing for Q4. Okay, the model at least loads on NVIDIA 6000 Blackwell Pro GPUs. The model is not going to load on 5090. It is just not going to, because 5090 only has 32 gigs of VRAM. And this is exactly the point that I was trying to make. Let's take a look. So if I go back, switch the GPU to devices 2 is our 5090. And let's take a look. So it will attempt to load it over here and you will see how it crashes. So it'll go all the way up, attempt to load 31 gigs right here, and it will crash and come back down. This is the point that I was trying to make. So let's go back and let's see the logs. So it says model failed to load because there was out of memory error, right? So it just wasn't able to load this much amount of model. Now there is a way to work around that. You can use two GPUs together, which is another reason why I wanted to show you existence of these two GPUs at the same time over here. But if you only had one RTX 5090 and if you are comparing apples to apples between one RTX 5090 and one RTX Pro 6000, of course you are not going to be able to do this, because the total amount of VRAM required to load a Q8 quantized model for Gemma 3 just isn't there for 15090. Okay, how do you load this model on two different GPUs? So the way to do that is you will just go back, modify the prompt, and you can just say that, hey, instead of loading it on just 2, I want to load it on 2 and 3. And if I hit enter now, you will see that both the devices will load this model. So 46 gigs of VRAM is now utilized. but the model is now successfully loaded over here. So if we send the same request back to this model, it is now going to be processed on these two 5090s. So as you can see, it is processing on both of them, and we'll compare how the prompt processing and the token generation look like now after it is done. Okay, perfect. Let's go ahead, take a look. Prompt eval time 3500 and token generation 40 tokens per second, which is about the same. Why is that? So one of the reasons why this is working so fast is because we have PCI 5. The amount of memory that is passing, or the amount of data that is passing through PCI 5 is insane. We are not restricting our GPUs to X8. It is at full speed PCI 5 working at its best over here. Okay, so this is all about llama.cpp inferencing that I wanted to show. And in terms of results, it was very uneventful. The results technically, I mean, if your use case is that you want to have a cheaper setup, and cheaper is just a statement that I'm making over here very loosely because each one of these graphics cards are close to 2K, the 5090s, and one 6000 is close to 10K. Two 5090s are still about half the price of this 6000. If you want not to spend so much on one 6000 Blackwell, you can still get one 5090 now, add on a second 5090 later, and then a third one later on. And you can incrementally build your rig. I mean, yes, of course, there are inherent advantages of having all the VRAM on one single card, but it still works. It works just fine for my use cases that I'm going to do. All right, now let's do image generation. And we'll be using the new Flux Context model over here. I will be using my own custom Docker image that I have built for this purpose. So let's load it on device 0 right now and then see how it goes. And then we will load it on device 2. So let's load this, and the ComfyUI is now running. You can see on the top over here, ComfyUI is running. Okay, now we have two options over here. Option number one is we can just access the ComfyUI's web interface directly from where we have defined this to be running at, right? So in my case, I have defined at 8188. And if I do a refresh, you can see that ComfyUI is now running over here. I can totally see why a new person will find all these different wirings and diagrams as a bit complex. How do we make it easy? So I have actually another UI that I built. Under the hood, this UI is using ComfyUI, but it makes things a little bit easier for us. All we have to do in this UI is choose any random image. So the random image that we just downloaded from internet, that Taj Mahal random image over here, very blurry image. Let's ask it to enhance details and make it higher resolution, right? And let's just send it and see where the model is loading now. So the ComfyUI is running, but the model hasn't loaded yet. And the model that we have is the context model over here. So I'm going to click generate. And this is the fun part. GPU 0 is correctly identified as the 5090 when we are accessing it via Docker devices 0. Okay, so our image has generated, and you saw it took a few seconds, 23 seconds to generate it. The reason why it took 23 seconds is because the first few seconds were spent in loading the model. What we'll do is we'll generate it again so that we can see how long it actually takes to generate the image and not to load the model, right? So the model loading time won't be in here. I think model loads in a couple of seconds, but still I want to eliminate that. So 13, 14, 15, and about 15.9 seconds is image generation took. This is absolutely awesome. I actually love this UI that I built over here. Of course, it is built with the help of DeepSeek R1. Something that people are usually, interested in is anime. So let's have it do the anime style and see what it looks like. And I can, of course, do all this directly on the ComfyUI's interface too, right? I mean, I can drag and drop these models and everything, but why to do all those complex things when you can build a simple user interface to do all this for you? Absolutely gorgeous and awesome. Right? Photo bombing. And I can also say that, hey, remove the girl from the picture. And this is what the context model is amazing at. It is not only intelligent, it understands things, it is able to generate things in an amazing quality too. So you will see that it will remove the girl who is photobombing the picture. Oh, it did not. It did not. Don't fail me, model. Okay, so let's remove the anime and I wanna remove this girl, remove the woman. Sometimes it censors it, so maybe using the word girl is censoring it, and just show Taj Mahal. Right, so let's do that. Okay, so it will take another 10 to 15 seconds, of course, well, closer to 15 seconds, which is what I've been benchmarking against the 5090. Let's see, 13, 14, 15, and right there, 15.7 seconds. Okay, so it did remove the girl, I think so, right? So all other people are here, right? Now the image is just as blurry. Its image is just as blurry. It removed her and filled in the details, right? So let's see. Wow, perfectly. Wow. It also put some trees over there. Oh no, trees were already there. So let's see if it filled in this tree. It did. It did. I think I'm just amazed that it created the blurriest picture and still fixed it. And if you want, you can incrementally now feed this picture to the model and then say, hey, remove everyone and just keep the Taj Mahal. And then it will be able to do that too. But anyway, what I want to show you is that this model context dev loads over here and close to 15.7 to 16 seconds. That is where it is sitting at. So just under 16 seconds is what it is sitting at. And I want you to remember that part. Now, I'm going to attempt to load this model on GPU 2. So let's do that. Control C, Docker stop ComfyUI will stop that particular Docker image from running, which will, of course, unload the model. Plus, it will also stop the Docker container, right? So it will unload the model too. Perfect. It is done. And then we will go back to our command. We will choose device 2. And you will see that it correctly identifies the GPU as 6000 over here. All right. So hit enter. And now it will run on this particular device. Now we are running this on RTX Pro 6000, right? So we'll send back exact same command and we'll see and watch how many seconds it takes for it to generate the image. So the very first generation, we won't count because the very first generation is the model loading time. You can see it is still loading the model over here. So this doesn't really count. We'll hit this generate again and we'll see the performance and the time taken. So you can already see that the model did get done faster over here. Of course it did. And I'm going to do generate again. And now you will see the real time difference between 5090 and 6000 Pro. So running this ComfyUI workflow, and this will be 12.4 seconds. And this is something that I have seen that works really, really amazing on 6000. This context model, exact same model, no difference over here. But on 6000, there is definitely a significant performance boon over here. Like 16 seconds versus closer to 12 seconds is what we are talking about. Right, I'm gonna hit generate again just to make sure. And I've actually been able to replicate this multiple times. So this is not an odd coincidence over here. On Blackwell 6000, it consistently generates closer to 12 seconds, whereas on the 5090, it consistently generates closer to 16 seconds. So there is a noticeable performance difference as compared to the LLM inferencing that we saw. We have a very noticeable performance difference over here. Okay, let's have some fun with some image generation over here. So here is Eiffel Tower. Let's get that. Or which one should we get? This one looks pretty. Okay, save this image. And what we'll do is so the JPEG file, and we'll come back to our particular UI and turn it, cartoonify it, right? Just that, just cartoonify it and send it and see what does this do. So in this case, because we changed the image over here, of course, the resolution and everything else has changed. So the time has changed over here. So we're not looking at the time, we're just having fun right now. So you can see Cartoonify. This context model is really, really good. Okay, let's do a claymation. And so that was nice. Nice. Okay. Really went back to its 12 seconds time over here. Okay. Let's change it to Family Guy style and let's see if it even does anything with it. And I've just given all those different system prompts over here for it to do this. So once you choose individual Family Guy, Simpson, and all these things, it just uses that particular system prompt and attempts to make it like that, right? So there's nothing fancy in this Family Guy style. It's just a pre-configured system prompt that you do not have to type in over here. Right, so let's do a Ghibli style over here and let's see. Again, 12 to 14 seconds is what we are looking at. And this would translate to a little bit more if we were to do the exact same thing on our 5090, of course. Wow, okay, pretty. Let me show you which model I have over here. So, and what's the quantization for it. So let's go back in the models. And you can see in the diffusion models, the one that I have is Flux One Dev Context FP8 diffusion model. So this is the one that we are running. We're not running the FP4. We'll do FP4 in some other video. And because these cards are specifically designed for FP4, but I found that the quality that I'm getting with FP8 is really amazing. Like both these cards were just perfect to fit this model on our FP8 Precision. So I don't see a reason for me to switch to FP4 apart from the fact that I want to try it out, but FP8 is just sufficient for me. Okay, if you want to see text encoder, which one I'm using, and the VAE over here, so all these, let me make a separate video. And in that video, I'll go over details of using ComfyUI and Flux Context and this particular UI. Right, so how you're going to use this particular UI, because there is a concept of API in ComfyUI, which I've covered in one of the previous videos, but the things have changed a little bit now. So I'll recover a couple of those things, give a brief overview of ComfyUI, and then talk about what the API for ComfyUI looks like, which is what enables me to build a UI on top of ComfyUI, essentially. But anyway, this is a high-level comparison between the text generation and image generation models and how they work between 5090 and RTX Pro 6000 over here. All right, guys, what did you think about this comparison? I had a ton of fun making this video. These two graphics cards are top of the line graphics cards. You know, the only thing in a way practically that differentiates these two cards is the amount of video RAM. 32 gigs versus 96 gigs is the main difference between these two cards. The performance is about the same. It's almost the same. There is no practical difference in performance, and it goes unnoticeable, let's just say that. The video generation comparison will be the next video. And till that time, please let me know in the comment section how you like this video. And if there's something special, something that stands out that you would like to see, I'd be more than happy to make another video based on your request. Thank you so much, and I'll see you guys in the next one.